Hi and welcome again to this chemistry lesson. We're looking at chemical energy changes, the rate of a reaction. In the previous video we considered collision theory, which we stated is that theory that a reaction occurs when there are, and this is the important word, successful collisions between particles. And that successful collision means that the particles are bouncing so hard, okay, in other words, enough kinetic energy is bouncing with enough kinetic energy so that there are successful collisions between particles. Now, how can we and that would be what we will focus on in this lesson. What are the factors affecting this? Factors affecting successful collisions. Okay, so that's spelled wrong. Successful collisions. In other words, if I wanted to increase the rate of reaction, I need to increase the number of successful collisions that occur every second, okay, which might mean I should increase the kinetic energy. Okay, so one factor that I can do to increase the rate of the reaction is to increase, let me do this colorfully, okay, is to increase the temperature. Okay, now why does that? Temperature. When I increase the temperature of a reaction, or the temperature under which a reaction occurs, I am adding kinetic energy. Okay, I'm adding kinetic energy. This excites the particles. Okay, kinetic energy. This excites the particles, and they are moving at higher velocities, and therefore a higher kinetic energy. So the increase in temperature translates or is converted into kinetic energy among the molecules. Okay, so that's one way I can increase the rate of the reaction, increase the temperature. And it's also the one factor that you can control that will always have an increase in the rate of reaction. Another factor that you could change is adding a catalyst. This will also always have an increase, no matter what the products are. Sorry, the reactants are. You're adding a catalyst will also always increase the rate of the reaction. But how does adding a catalyst actually have that effect? Well, we also did look at this in a previous video, and again, it's about the intermediate molecules, the intermediate state. Okay, when we add a catalyst, the catalyst does have an effect. It does produce intermediate molecules, okay, but in the end, so if we have our A plus B, and let's say C is my catalyst, okay, then I would have some molecules reacting with my catalyst, okay, plus some molecules, of the other product reacting with my catalyst, and then in the end these two molecules would be able to interact with one another to produce a product, and yet leave the catalyst back in its original state. Okay, now the internal energies of these intermediate molecules is less than the other intermediate molecules that would have formed without that. So if I were to look at my energy diagram, okay, we know it looks like this. okay? And the moment I add a catalyst, the activated complex isn't as high, okay? A catalyst reduces the activated the height of the activated complex, which means less energy needs to be added, and because I need less energy, okay, to form that, I already have enough kinetic energy to not have enough, more of the molecules will have enough kinetic energy in order to produce these intermediate processes. So if ever you are asked, how does a catalyst affect the rate of reaction and why? Well, a catalyst increases the rate of reaction, and the reason why is because it reduces the amount of kinetic energy needed for successful collisions to produce intermediate molecules. Okay, that is how a catalyst is affecting it. Now, these are the only two factors that we are going to look at that are general. In other words, it doesn't matter which products I have. If I increase the the temperature, it would increase the reaction rate because all molecules are getting extra energy. If I add a catalyst, it increases the reaction rate because the amount of energy needed for successful collisions are less. Okay, now we're going to look at more specifically if I'm working with specific types of products. Let's first look at working with solids. If one of my product is a solid, okay, let's look at this solid right here. So here's a piece, whether it's metal or whatever. I'm going to just look at a solid piece of thing, okay? And solids are three-dimensional, as I suppose all things would be, okay? And let's say this one has a side length of 2 by 2 by 2. Okay, it's a cube 2 by 2 by 2. Okay, and what I specifically want to look at is the surface area. Okay, if it's a cube, all of the surface areas are the same. Okay, and I'll explain to you just now why I'm looking at the surface area. But this one's surface area, the total surface area, would be 2 by 2. This is 4. A cube has 6 sides. This one in the front, that one at the back, a top, a bottom, a left, and a right. So in total there's 6. So I've got a surface area of 24. Now, why am I looking at the surface area? Well, it's fairly easy. Let's say I were to drop this solid in a liquid. Okay, the only successful collisions can occur on the surface because the liquid is only in contact with the surface. So if the liquid wants to interact with this solid, it can only interact with the exterior, the amount of the solid that is actually in contact with the liquid. Okay, and that goes the same with a gas. If I'm passing a gas over this thing, again, the gas can't get to the inside of the solid because it's solid. It can only interact with the surface area. So what I need to do in order to increase the amount of successful collisions is if I can increase the surface area, I would increase the number of successful collisions. Now, how can I do that? Well, let's just cut this thing in half. What happens when I cut it in half? So there, I've cut it in half. Okay, so there's my 2 halves. Okay, not very prettily drawn. There's my 2 halves. Now it's still a 2 by 2, but now since I cut it in half, I cut it down here. If you can't see it due to my poor sketch, it's now a 2 by 2 by 1. Okay, so this is still a surface area of 4. Okay, and the back is still a surface area of 4, but now the sides, that is a surface area of 2, 2, 2, 2. So I've got 2 4s, which is 8, plus 4 2s, which is also 8. Okay, so this thing itself has a surface area of 16, but I've got 2 of them. Okay, so this one has a surface area of 16 as well. So now I've got a surface area of 32. Okay, so the moment I cut this thing in half, I'm exposing more of the thing. Where I cut, those two sides that now exist because I cut this solid in half never used to have never used to be part of the surface. So if I were to cut this thing again, so I'm cutting it there again, I'm exposing part of the solid that wasn't before exposed. So the ultimate would be is not just to, well, yes, cut it into smaller pieces. Okay, so if I cut into smaller pieces, or the ultimate would be the ultimate cutting into smaller pieces would be to grind into a powder. Okay, if I grind something into a powder, I am actually that's probably the most surface area I can expose, because I'm literally taking the smallest part of that solid that I can possibly make out of it when I grind it into a powder. Why does that work? Because I'm increasing the surface area that is in contact with the rest of the products. So when I'm working with solids, that's one way in which I can increase the amount of successful collisions, by exposing more of the surface area, by grinding it into a powder, or at least cutting it into smaller pieces. Okay, what about working with a gas? Let's go to this side. Okay, working with gases. Now, whenever we're working with a gas or with gases, we're working in closed containers. So here's my container, okay, and it is closed. And in here I've got my particles, okay, the gas particles. Now, if we consider these particles hanging around here, remember the particles, especially in gas, are always moving. The particles are moving around. Now, what would happen if I take this same container with the same amount of gas in it, okay, and I were to half its volume? Okay, if I were to half its volume, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8, okay, 2, 4, 5. Now I've got the same amount of molecules, but there's less space in which they can move around. Now here, the likelihood of them getting in contact with another one is probably not that low, okay, but here that likelihood is higher, because there's less space for them to move around, and there's less area around the molecule that's not inhabited. So for example, around this one, if I can maybe draw a neighborhood, and this is just an illustration, okay, there's about that much neighborhood around this one where he doesn't have a neighbor, okay, while if I look at him here, that neighborhood is much smaller, which means the likelihood of him moving around and getting in contact with another molecule is much less. So what happens if I decrease volume? So when volume is decreased, that's synonymous, okay? In other words, that's the same as saying I increase pressure. Increase pressure. Pressure is defined as the amount of substance, of a gaseous substance in a certain volume. So when I decrease the volume, I'm increasing the pressure, okay? So if I increase pressure, I'm also increasing the likelihood of successful collisions, because, and the reason why is because there's less space available for unsuccessful collisions. Does that make sense? I'm taking away the possibility of unsuccessful collisions by taking away space where nothing can happen. I hope that makes sense. That's the best I can explain it. Now, another thing about increasing the pressure, and you might have noticed this if you take your deodorant. Okay, so there's a deodorant bottle, and if you spray it under your arms, okay, there's your arm. Okay, have you noticed how cold it is? Why is it when this thing is at room temperature, when the gas actually reaches your arm, is it so cold? It's really very, very cold. The reason is actually quite simple. The energy that the particles have under pressure is higher than the energy they have when there's less pressure. Okay, so here they have the same amount of energy than they would have at room temperature, but the moment you release them into the atmosphere, okay, they have less energy. So the energy they used to have, they now have less energy, and that is why they feel so much colder. So also when we increase the pressure, we're also increasing the energy of the molecules as well, the kinetic energy. So that also has a major effect on the reaction rate when we are increasing pressure. So that's the second thing. The third thing we can, no, we're on the fourth thing we can do is when working with gases, we can increase the pressure. And then finally, if we're working with solutions, so for example, very often our acids are dissolved in okay, so again, this time it's exactly the same. It's not a closed container, it's exactly the same. We've got a liquid here. Okay, this is a liquid, and in my liquid, in order for my liquid to interact, or this liquid is something like water, and in order for my one substance to react with other substances, I have to dissolve it. Okay, it's called an aqueous, I think that's how you spell it. An aqueous solution means I'm dissolving my my one reactant into a solvent, and there it is. Okay, these little pink dots would be my reactant, the blue would be my solvent. Okay, and again, similar to when we worked with gases, is if the fewer of these pink dots there are, okay, the more unlikely it is. Now remember, the pink dots aren't interacting with the blue dots. Let's choose a different color. The pink dots would interact with the yellow dots. Now you might not be able to see, okay, but the pink dots would react with the yellow dots. That would be the other product, for example. Now, in order to increase the likelihood of this reaction, all I need to do is simply increase the concentration. The concentration. Now, the concentration is your solvent, the ratio of your solvent compared to your reactant. I keep forgetting my C in reactant. Okay, in your reactant. Okay, so in other words, if we want to increase the concentration, that means we either have to decrease the solvent, in other words the amount of blue dots, or we have to increase the reactant, keeping the solvent the same, or both, of course. Okay, so in other words, basically what it means is we've got one of two options. Either we can have the less solvent and then the same amount of reactants, and then the same amount of the other product, or I can, of course, in this, the same amount of solvent, just add more of my reactant, and it works exactly the same because there are more of the reactant actually available, or because the space wherein the reactant find itself. So here I've decreased the amount of solvent. Here I've let's do it like this with color. here I've decreased the amount of solvent, and in this one I increased the amount of the reactant in my solvent. And in both cases, in this one, by increasing the amount of a reactant in my solvent, I have increased the concentration, but I've increased it by adding more reactant, and therefore there's more possibilities of successful collisions because there's more reactants available. In this one, I've decreased the amount of solvent and I've increased the amount of the possibility of successful collisions because I have actually reduced the space. Do you notice that? The space wherein the reactants find itself is reduced. So here there's so when there's more solvent, there's a likelihood that they're hanging around somewhere where they can't interact, while here there's less space available. So basically it comes down to, in these, if I had a crowd of people, or if I have a room with people in it, okay, the bigger that room, if I increase the size of the room, and it goes the same for this as an explanation for gases, if I have people in this room and they're running around, the likelihood that they will run into each other is, well, whatever it is. But if I decrease the size of the room and I still have the same number of people in it, okay, notice that the likelihood of them running into each other is much higher, and that would be the same effect as in gases decreasing the volume, okay, or in solutions decreasing the amount of solvent, okay, that decreases the space where the molecules have to move. Okay, I'm sorry if I repeated myself a lot. This is such a simple and common sense type of topic that I really want you to get it, because once you get it, you don't even have to study this at a later point. It just makes sense. So hopefully you learned something in this lesson. Thank you for watching. We'll see you in the next video.